Okay, textures now. The images you see on this particular image, you see in the upper right hand corner, we have Woody. You can see his polygons. Down here, you see the bunny. He's got all those bumps. Some of those are probably from normal mapping. We'll get to the particle system up here by the end of the course, hopefully, now that we've accelerated things a bit. But in the bottom right hand corner, you see this character with lots of textures. Let's see how those textures work. Um, we could make smaller and smaller and smaller polygons, but as we know, every polygon costs us money. Now, one of the things that we do in our houses is we put wallpaper up on the wall to add a whole bunch of detail. So we're basically going to do the same thing in computer graphics. Again, cheat, cheat, cheat. Everything we do is cheating. So what we're going to do is essentially take decals and stickers and we're going to plonk them onto our models, and that is a process called texture mapping. So OpenGL triangles, we saw that we could uh, add color to our vertices. We were able to do this. We added RGB for each of the points, and we were able to interpolate it. And we actually wrote the scan converter for this that allowed you to actually write the code for this triangle. Um, so this is what our assignment did. We had a flat, then we went with interpolation, textures. What are we going to do? Well, we have these images from the real world. We have these beautiful cameras in our pocket, and we can take pictures of textures and everything. We could use that to add detail. So, for example, we have bark, and elephants have wrinkles, and then metal has this pressed look to it. We can do all of this stuff. We can add it to our textures. We can actually make things into polygons as these modular walls, but we can also cheat, and we'll see how we can do that. So here's an image. It looks like it has a whole bunch of bricks on it. It's actually a 2D image. It's just a photo that I had ChatGPT generate for me. And we'll see as part of this assignment, you're going to see this texture on your model. It's actually, if you do a git pull on your resources, this will be one of the models in there. But it's just two triangles. What? How do we do that? Two triangles and all that detail? Well, this is what's going to go on, is that we're going to load images into our computer graphics engine, and then instead of rendering the color of a pixel based on the interpolation between colors at the vertices, we're going to use a coordinate from that particular position. We're going to go to an image and get the color from there, and we're going to splat it onto the polygons. Textures are drawn by having a picture and sampling. And sampling means taking a sample. You know how you would take, if you're at an ice cream store, you take a sample of ice cream. So you take it and you get the flavor of that ice cream, then you can go take another one. That's exactly, not exactly, but it's a metaphor for what we're doing in this texture sampling space. Our shaders, our hardware, our GPU is going to do this for us. So we will probably do a little bit of this in class, and we will do the painful thing about sampling a texture and seeing how difficult it is and how complicated it is. But we are going to let the hardware do it. So once again, how do we get the hardware to set up for this? Well, the hardware is actually built for this. So we are going to need, for every position in space, a UV mapping, a two-dimensional mapping. And so for a square, it's quite easy. I'm just going to say U goes from 0 to 1, and V goes from 1 to 0, 0 to 1 up here. And so if this image has 256 pixels in each direction, halfway through here, I'll go to pixel 128, 128, and I'll get the value for that, and I can slap it up. But how do we get that? Okay, so if I can compute a UV mapping for my 3D, for my polygon, then I can give you the color of that texture. You can say, hey, I have UV of 0.5, 0.5, and I'll say, oh, that's a kind of a dark gray, dark brown thing there. So in the animation business, there is this idea of mapping. Every polygon that you generate has a UV map on it, has a UV coordinate, and then that indexes into a polygon. So one of the models that you'll see in this next assignment is a cube. It has 6 faces. So if I want a cube that's a die, I can actually map it out this way. I can say, well, this particular face here is going to map to this. There's a 3 on the bottom, there's a blue here, but notice this one here is the back face, and then this little single dot here, which is over here, folds up and goes over here. So if my texture has a coordinate of 0, 0 to 1, 1, then this particular square here goes from 0, 0 to 0.25 in the x, and from 0.333 to 0.666 up here, and then 0.25 to 0.33, and 0.25, 0.666. And so you can see how these things map on there. So again, we're going to decompose this problem into a problem that's simple to deal with. Well, how are we going to do that? On a per vertex basis. So we're going to solve this problem of painting textures over objects by doing it on a per vertex basis. Remember, computer graphics is just about rendering triangles, but doing it really, really, really fast. So we're going to unwrap our model. We're going to do the UV unwrapping. If you think about this, look at this animation on the right-hand side. We have this model, and we map it into a 2D space. So each one of these objects here, or each one of these polygons, gets some UV coordinates such that when I'm rendering this particular triangle, which is this triangle here, I use that data. And so the textures make no sense whatsoever. And if you look at the lion texture, the lion in your resources folder, you'll see that the lion texture has this weird look. You can also look at the cube texture, the capsule texture, the triangle and the square textures. They're fairly straightforward, but the other ones, you can kind of see this unwrapping thing. In objects like Blender and Maya, you can paint UVs onto the space. In fact, what they let you do is they will generate a UV mapping for your object, and then you can paint directly onto that object. And what the system does is it then paints into the UV map that is generated. So you actually can see, you can go in here and paint this like fur stuff here, this the red here, and that all works. And then we as computer graphics programmers, we just get that data, and we don't care how this particular image was mapped out. All we care is that there is there's a strong relationship, or very clearly defined relationship, between this object and this object. So you can see that the green part of this character maps to that, and it's kind of symmetric. So this part here will also map to kind of the same as that, and instead of that. So you have these things, and notice that there's different textures here as well. You got the big texture, and then you've got a logo here, and then you've got some other stuff here. You could have multiple textures for character. WebGL2 allows a minimum, is guaranteed to give you a minimum of 32 textures per object, which is quite a huge amount of textures. In .obj, we can actually specify for each vertex what these UV coordinates are. That's what these VTs are. In the next assignment, I'm going to give you the code that reads the vertex texture and the vertex normals and builds out the vertex buffers. You've done that already for the vertex positions. You're not going to learn anything by doing it again. I'd rather have you move forward and to get some more funky stuff happening in our computer graphics. So the next assignment is going to be doing more about camera. So usually this is done by the artist. We as programmers don't necessarily get involved with this. So how do you map these things? We do know that if you have a spherical object like this, there's all sorts of ways you can map it. This is kind of the typical one that we do, so that the North Pole, which is actually a very, very small part of it, becomes this really big thing. So countries like Canada get blown up. We are a big country, but we're not as big as it actually looks here. This one here is a little bit more accurate. If this thing had been shrunk down right to the bottom, then it would be even more accurate. This mapping has been studied for years. Cartographers, basically, there is a whole science behind how to do these mappings. We do it on our computer graphics objects. We do it like piece by piece. So we'll have like this part that maps to a square texture. This one is so it's not. We don't need to get it exactly right as in the same way that the mathematicians are trying to do. But we really want to have a good texture that when you look at it on the object, it looks good. There are a whole bunch of projections and stuff like that, but we're not going to worry about that. What we're going to worry about is taking, we're going to take textures. But just so you know, here are some projections. This is a planar projection. Our texture is projected onto the cube. Notice how it stretches out here. We really don't want to do that. We should fire that artist. Then we have this one here, which is a triangle. This actually kind of looks good, but it doesn't stretch it out. So triangles are fairly straightforward. And look at this one here. It looks great around here because there's continuity. But between this point and this point, the 17 and 37, you get this discontinuity up there. As I said, these mappings, we don't really do it. We let the artists take care of it. They paint it on the objects, and that takes care of it, so we don't have to worry about it. If you notice, these mappings, which are what the mathematicians are looking at, look nothing like this mapping here. Where were we here? This mapping here is nothing that a mathematician would come up with. It's more what an artist came up with so that the textures could be rendered onto this object in a nice way. So we're going to skip over this one, the seams look ugly up here, very little distortion. And then there has been some research on how to do this automatically. The artists, tools that help the artist do this, you can go look at this video. It's in the slides. You can go look at it, but you can kind of see it there. Okay, so we've got this texture, and we got an UV value, and we go get the data, and we're done, right? Well, not quite, because it gets a little bit more complicated than that. So we're going to build this thing called a MIP map. MIP stands for Multum in Parvo, many things in a small space. And we're going to take this, we're going to take the average of that, we're going to make this one the average of that. So each of these pixels, each of 4x4 pixels, 2x2 mapped into one here, and 2x2 mapped into one here, etc., all the way down. So these are our level of LODs, level of detail, and we'll see how that comes up in a second. Basically, if you think of pixels on your screen as little holes, they actually map into larger and larger spaces. Let me just pull up my GIMP here and show you. I can show you this really quickly. It's kind of cool. So let's go get rid of that. So if we think of, we have this object down here, and it maps to a texture. So the UV on this is basically 0, 0, and 1, 1. And let's say we have a screen here that has 4 pixels on it. Let's say 4 rows of pixels. And then I'm going to take this pixel here, so it's kind of a circle there, and my eye is here. So let's put my eye here. So I'm going to do, this line goes there, and then this line goes there. So that maps onto a space about that big on my uh, texture. Now you'll notice that this, let's say this is a 1K by 1K picture. This is going to be a lot of images, but we just basically, what we do is we do this, we just draw a line from there and we take a spot here, but that spot may actually be representing about 100 pixels. So what we do is we represent different frequencies of this. So we would have a 1K by 1K, 512 by 512. And so in this particular case, when I get down to, let's say 4 by 4, then I have 1, 2, 3, 4 pixels, and like this. Oops, that's a straight line. And so now this value here is actually kind of representative of the average of this space there. So what we're going to do here is we're going to so the pixels here represent are closer. So when I project my pixels, sorry, the texel, the floor here is closer. So when I project my circle of my pixel down onto it, it's fairly small. And so I'll use a very high definition image. And so you can see lots of detail here. And then on this one and this one and this one, you'll see that we're using different levels of this level of detail pyramid. And so things get blurrier as you go further out. This actually helps us. It simulates the real world because as thing gets further away, the receptor in the back of your eye picks up larger and larger blobs. So at the very, very far distance, trees turn into blurry things, etc., etc. So what happens if you don't do this averaging? Well, what happens is that the numbers that you pick become random. So you get this kind of, it's called aliasing. You get this kind of noise here that doesn't look anything like this texture here. But you see here it kind of slowly blends into something that's a little bit more pleasing to the eye. So it turns out that in our graphics hardware, this MIP mapping is actually built in. We specifically, we load an image and then we say generate MIP map, and it will generate the MIP map, right? So that's something that we do in our preload. We will make sure we only do it once per draw call for each texture. I think my code actually does it for every render, but we'll fix that. And then, but what you do is you do get these images that go nice and blurry at the end, and they don't look like this, right? This is not appealing because as you move your camera around, this will all shimmer and go brrr, and that's not very pleasing at all. So this is, again, see these kind of things in the background as you move your camera around, you'll get this noise interference and it's highly disturbing. And so with MIP mapping, we're essentially what we're doing is we're taking averages over bigger areas of that texture because that pyramid of textures actually takes the average as it goes up. And there's a whole bunch of research. In fact, my PhD thesis was something to do with more sophisticated ways of doing this. So what are the trade-offs here? Well, you have to store more data. You have to store these different levels of detail, but it's basically twice your storage because if you think about it, you take your image, then you store a quarter more, then you store a quarter more of that and a quarter more of that. So it doesn't actually equal to two images, so you build your hardware around that. The about 1.5 times is the cost. We do need to perform anti-aliasing, which we could do by sampling multiple pixels, but that costs more money. So memory is actually quite cheap. So we're doing, we've solved the problem by just adding more memory to our graphics cards. And in general, for most of what we do for real-time graphics, that is good enough. So you can see this here. You have this close-up area, and then you have the far away difference where it's all blurry, and then you can also depth of field. You can see in these two images on the right hand side that you can focus people on the right things. Again, this is a reimagining of how cameras work. The maps aren't physically correct, but they are a good physical approximation to what we see. So how do we do texturing in WebGL? Now we know what we need to do. We need to take an image and we need to add it to the hardware, and then we need to tell that hardware to use those colors when it renders those pixels. Okay. Well, we have texture environments. As I said, WebGL allows up to 30. WebGL 2 provides a minimum of 32 texture samplers. And so you can basically, your shaders can use these in any way. You just have to set them up as textures. So now we've got this third object. We have uniforms, we have vertex buffers, and now we have textures. And so we get that there. So we are going to get some code to try and render a texture in WebGL. We'll walk through the steps, but we need some more abstraction. So in canvas.ts, there's this function, set up texture. What we are going to do is, first of all, we're going to tell the hardware where are we going to store the UV values for every triangle. Remember, we have to have those UV values. We're going to feed them in per vertex. We're going to interpolate between them, and then the fragment shader will use that to get the color. So we actually have to tell WebGL where to put the data. So we do that here. And then we go through here. You remember how we said colors are interleaved with positions? Well, we're going to do the same thing here. We're going to add our texture coordinate. It's 2 of type float. And we're going to have a stride for the whole vertex. If we have position and texture, then this vertex stride will be 5 times the value of this floating point here. And then you have an offset. So if you have color and then texture, the model texture offset will be 3, because the texture starts after 3. And so you can have normals in there, you can have colors in there as well. But for this particular, at this point, we're just dealing with the texture offset. The sample solution that I'm giving you actually builds vertex buffers for positions, textures, and normals, which we're going to need for lighting. So that's coming up as well. Okay. And so what we now do, we say, okay, so this is the input. This is where all of our UV data is coming from. Now we're going to set up, the texture. We're going to prepare to give the hardware the values for the texture. So remember, with a vertex buffer, we say we're about to give you a vertex buffer, and then here it is. We're going to do the same thing for textures. So the first thing we do is we say, create a texture. And if we don't get a texture, we're going to bail out of there because we haven't given it a texture. So we're going to start now. And we select one of our texture units. So texture unit 0, since we only have one texture. Then I'm going to activate that texture, so that will make it the current activated texture. So any texture commands I issue will be applied to that texture unit. So I bind a texture, a 2D texture, to that texture, and then I set some parameters, which basically says that this is a 2D texture, and it's going to, this is the S and the T. So typically we don't use UV, we use S and T. They're interchangeable. WebGL uses S. And here we're going to say clamp to the edge. So if this value of S is greater than 1, we will just clamp it to 1. And if it's less than 0, we will clamp it to 0. You can actually wrap it so that you have periodic textures, or you can just clamp it. In this particular case, we're going to clamp it. And then we're going to say, how are you going to interpolate between the 4 samples, or if you're taking multiple samples, how do you do that? So let's go there. So here's where we say, what do you do when you come to the edge? And here we say, how do you interpolate? What are you going to do if you sample a texture between two pixels? How do you calculate the value between those two? And then here's where we load the data. So we here's our file loader. If it's undefined, we bail. If the data is undefined, then we bail. But now here's where we go back into our program. We get our texture sampler in the code. You'll see that in a second. And then we set that texture location to be that. And so then now we're going to set up the image, and we say, this is where we give it the data. So we go, there's our data. Remember, we computed it here, and then say, here's the data, off you go. And then we go here, and then we generate the bitmap. Now, we don't have to do this, and I would advise that you play with this with and without the bitmap. Just comment that out. In fact, we'll do that in class. Why not? And then we can see what difference that makes. So there we go. We've set up our texture. So we don't have to code bitmaps. We'll play with them a little bit in class, but for the perspective, you don't really need to worry about that. So I've added the code to load a texture. And so what we have, we've parsed the PPM file, we've generated a texture, we've bound. What are we missing? Shaders. Two shader coordinates, we've already put them into the data, and a modified shader, two modified shaders actually. We've already done that one. That was, ignore that for now. That's a duplicate slide. So we're going to have a texture quad. So here's our texture quad, 0, 0, 2, 1, 1. And in class, we're going to go through and you'll see how this works. We're going to pull up our frame buffer and we're going to add UV. Well, not all of the thing, but I'm going to show you how we do interpolation and how that features in. We'll add a texture to our frame buffer, etc., etc. So that's what we're going to do. The texture coordinates for each vertex are specified to the right. And so here's a sample where we could have gone this path where we go specify the left vertex position, the color, and the texture. So you have 3, 3, 3. We're not doing that. We're not doing color. It turns out that once you start adding textures, you don't really want color on your vertices. It just saves you data. So in our particular case, it'll be this followed by 2, and you'll see that you can get that data from the object file. So here's OpenGL, but remember OpenGL is just WebGL without the dot. So here we basically set, we're saying we're going to do a attribute array 0, 1, and 2, and then we set a pointer for these pointers of 0, 1, and 2, and we say these are the types of things that you have. And then, so here we are, we're mapping off. Notice that the offset changes here, offset changes here, and the offset changes here. And it's the same thing in TypeScript. You do that, but we're not going to be doing this one in our code because we're just going to have positions and textures. Okay, so now the shaders. So we get the position of our, we set up our uniform for the textures. So textures are uniforms. They're kind of a slightly different for uniform, but there you go. We do that. And we're going to pass the texture coordinate through. So in our vector shader, we are going to have an input of vector 2 texture coordinate right there. And we're going to take, we're going to say we're putting a 2-dimensional vector out. We're going to call it texture coordinate out. So this is vertex texture shader. In our program, the names of the vectors tell you what attributes it's using. So the final shader, which you have there, is going to take a vector and a texture coordinate, and is going to take a model matrix, view matrix, projection matrix, and notice, so we've make this more complicated, And again, we pass the texture coordinate through. So we basically rename this texture to be that texture there, okay? Now the fragment shader for texture, we had we had in our previous shader we had in color, and we would just say color equals that. But here we basically say we're taking a value in, which is a vector of 2. We have a uniform sampler. There's our uniform, and there's my texture sampler. And so then I go and I use this. I'm flipping my Y's because all of my images are upside down in this particular data set. And I've made sure that all the images in the resources directory are upside down. If you do load an image and you notice that your texture is upside down, you can flip it in GIMP and re-export it as a PPM file. If you want to use any other image, just load the JPEG into GIMP. You can export it as a PPM, and then you'll have new textures on your things. So lots of commands. The web is your best friend. ChatGPT also great help. This is a very standard set of boilerplate code, and so you'll see the that Copilot helps you a lot when you do that. So we will have a plane with 2 triangles and a PPM image displayed on it. You can change the image and stuff like that. But we're going to go through kind of a hands-on exercise of this in class. So please understand all of the concepts and then come ready to class to dig into some hands-on exercises with the computer and without the computer. You're actually going to be drawing things by hand for the cameras. Anyways, that's it. Textures. What do? A picture is worth 1,000 polygons, because instead of adding a whole bunch of polygons, each one with like colors on the vertices, and we move them around, we're just going to we're going to cheat. That's what we do. And we're going to take an image and we're going to wrap it around that object and say, there, we're done. It looks really way more complicated than it used to. Okay, that's it. Thank you very much. And I will see you in class on Thursday. Looking forward to it. Bye.